So let me now go. Thank you again to everybody, organizing committee, and the authors and the presenters and attendees for coming to the conference. Let me move now to the next step. So let me introduce Ivica Crnkovic, Professor of Software Engineering at Chalmers University in Gothenburg, and Director of the ICT area of Advanced at Chalmers University, and Director of Chalmers AI Research Center, as you can read. We have been knowing since more than 15 years. We started a double degree program called GSAM in 2006 with University of L'Aquila and Bree University Amsterdam and Mallardalen University when he was working some years ago. It has been always a huge pleasure for those of you not knowing Ivica. If you don't know Ivica, it means that you don't come from this community, first of all. Okay. He has been, I would say, one of the co-founder of the CBSC symposium, Component-Based Software Engineering. He has been writing many books and articles. He has been really guiding, I would say, the component-based software engineering community first, and then moving to other communities and to other aspects of software architecture. Now with his group, he's very active in AI engineering. We had a meeting a few weeks ago to clearly understand what they are doing. So it's quite impressive. I'm sure that the presentation will be really excellent. Just a final word before giving the space and time to Ivica is the following. I was thinking to one word to say about Ivica. I would say only one thing: a model to follow. I always find him, even if extremely busy in many projects and education tracks and international projects with students and the research projects. But even in this, madness, because that's what it is. Most of us know what I'm talking about. He has been somebody where I could send an email, and this a lot of people know, at 2 a.m. and get an answer in 5 minutes, even if it was running, hundreds of tasks in parallel. Always friendly and always polite. So this is something not trivial, honestly. And I want just to, you are one of my model, honestly. And thank you very much for coming and providing your keynote at the EXA 2020. And then I will stop sharing the screen so you can take control Ivica and share your presentation. So we have a total of 35 minutes that we can use a part for the presentation and part for the question. For all the audience, please start typing questions on the chat. I will monitor the chat and I will collect questions, and I will pose the question to Ivica immediately after the presentation. So please, Ivica, take the scene and introduce yourself and start your talk.
Oh, thank you very much for really nice wording. I feel touched, and I must say that I'm very, very happy and very honored to be invited as a keynote. At the same time, I'm a little bit sad because I'm not in L'Aquila, because L'Aquila and people there it's so beautiful. I'm always so happy when I can visit you, but this time was not possible. So that's what makes me a little bit sad. But at the same time, I'm also happy because we have this possibility with the communication, which really works good. So I will share my screen, and I hope that you can see it.
Yes.
Okay, so that's good. So what will I talk about? You see, it's a little bit big title, but basically about new questions which we come in software engineering, and part of that in software architecture, and which is related to new trends in AI development, which is taking place everywhere. And as Henry said, I'm from Gothenburg. Originally, I'm from Croatia, and I was impressed by the pronunciation of my name by Henry. It was really well done. When we are talking about artificial intelligence, there are a lot of things, but the most focus today is on one part of artificial intelligence, and that is machine learning. And that's what will I talk about, or refer to that part of artificial intelligence. And then when we are talking about machine learning, there are different types of machine learning. Then I will also mostly talk or refer to a part called supervised machine learning, which is oriented in that sense that you have like objects, and you have different properties or features of that object, and by getting information from the features, you recognize the object. So that's the basic philosophy. And the process of training is going like that you get a lot of examples of the objects and their features, and then that's the basis for the recognition of the new objects. And there are, you know that there are a lot of talks about AI and in recent year, and also there are also many visible success stories about AI. It's in many different domains. I can just mention like traffic, we're still under developing, but already a lot of results achieved. Medicine, robotics, finance, health, space. You wouldn't say, for example, in the space, I know some research projects which are searching for dark matter. So that's dark matter is something which you cannot see it. Can you get? Is AI is used machine learning to find the behavior and characteristics of that dark matter. So practically there is no area in which AI have been used. There are some warning examples. You all remember the case, which was a tragic case when an object, the bicycle, was not recognized by the system, and that shows that how such system can have severe consequences. What was the cause of the error? It's still not known. Is it the AI part, or is it some other parts? But according to the test, the object was seen by sensor, so there was no problem in the sensor, but simply was not recognized. There are some other problems which shows that we built in our AI systems the bias which we have as a society or a group of people or something like that. So it's not a problem with the programs itself, but the programs are built in the bias information which is not a proper one, or which is not the one we want to use. So this was the case in Amazon, which had like AI program for classifying recruitment candidates, and they were based on the people working in Amazon. And after a while, it was recognized that the system was biased against women. So they were systematically classified on the lower level. And why? Because most of the people working at Amazon and some other IT and technology companies are men. So we have in the program built-in biased information. Then, of course, the system has also showed some other things that they are not so accurate, and maybe we can think about this. And sometimes this is good. For example, World Cup 2018, all predictions were wrong. So, and personally, I was quite happy because of that wrong prediction. So we can say that there are many challenges and many problems within AI itself, but many problems are related not only in the AI nature, but it's also related on the way how we develop AI-based systems. So here I would like to talk about what are the challenges, what we have seen, the challenges which appear today in AI-related development. And the questions related to AI, you can maybe divide them in two categories. There are many questions which are non-technical character. For example, who is the owner of data? What are the ethical aspects of using data? Who can use data? Who can, in which way data can be used? How can we allow a machine to decide? And how to interpret the result from the decision from the AI models. So these are the questions which have not technical characters, but then of course there are plenty of questions which have technical characters. How to efficiently collect, store, process, analyze, present data. How to efficiently build the AI-based systems. How to ensure enough resources. It's a computational resources, storage resources, timing constraints. Then how to ensure dependability or trustworthiness of such systems. AI by its nature is statistical character, and it's based on the probability. And so how is that related to trustworthiness, to dependability, to safety, to the security, to reliability, for example? What kind of software architecture are needed now when we have AI-based systems? Are they the same? Can we use the same architectures, or as new architectures required? So in general, we could ask the question, what kind of engineering support is needed for such type of systems? And I will discuss that, showing, starting with just making a basic, showing the basic process in what we have in the development, machine learning development cycle, which consists basically of one iteration loop when you create models and train and evaluate, and when the model is satisfactorily good, then it can be included in software, in the systems, and that's based on the data which have been assembled before starting the training. But then in the operation, when the system is running, the new data is collecting, and then again there is this outer loop which leads to improvement of the system. And that's when people are talking about AI development, are mostly talking about that part of the process. But if you look in the entire life cycle, and that is a citation from Google, from a paper from Google, then we can see that this machine learning coding is actually very, very small part of the entire process, or all the efforts you have to put to build up AI-based systems. And how does it look like? I will show you on one example, using a cyber-physical system, example of cyber-physical system, concretely like a car, which of course has some additional requirements than maybe web-based applications. And if you look at such a system of today, so without AI, then already we have quite complex software built in this cyber-physical system. Now I will talk only on the part which is related to controlling the engine, machine, the driving. And we have a lot of sensors and a lot of computational units, which are basically collecting data, receiving data via sensors, analyzing, processing this data, and control the system. That's what is going on. And sporadically sending data to the development environment, which typically is cloud computing, based on cloud computing. And of course, this is done sporadically. mostly in the workshops. For the modern cars, this is more often, but it's also sporadically. And then we have the development environment when the system is actually evolving, so fixing and improving, so the standard way of development. And then of course we have a process of updating the system, deploying it in the target, which is also ongoing sporadically. And how architecture do we have for that? This is the architecture, typical architecture of today vehicular systems. I'm talking about this controlling the engine part, and you can see that it consists of a bus, which one or several buses, which connects, which is using for connecting the information, and then separate subsystems, electronic control units, which are via sensors and actuators connected to the electromechanical parts of the machine. So receiving data and controlling the machine. And you can see this architecture is quite good because it enables, to some extent, very good scalability. To adding new function, you add a new ACU and the new software which is running in this subsystem or electronic control unit. And if you look at how the components or specifically services are implemented, then we can distinguish two types of such components, those which are like basics, which are doing like basic control on particular devices, but then there we have complex components which are doing some complex function. For example, stability of the car, use a lot of signals and send a lot of signals to actuators to enable this possibility. And in this case, we have a situation that one component of our service is actually distributed on several subsystem or control units, and also sharing with other components on the same executional unit. And what does it mean? That it means that we have like shared resources, both computational resources and network resources, and this is basically one of the main challenges in development of such systems, because we want to optimize the resources because of the production cost. At the same time, we want to have enough resources that enable exchange of information and the computation. So basically what we have here, the challenges are related to real-time requirements, to share resources, and resource constraints. If you look at typical architectural solutions, software architecture for such systems, it's a layered architecture, like a classical layered architecture with the lowest layer top on hardware basic platform, then middleware for the communication, and then different subsystem providing specific functionality. And if you look at particular subsystem, then typically we have a component-based approach in which we have components providing some computation and mostly using pipe and filter style, because that's the most optimal way how to process the streaming data, and also very good for prediction of timing and some other properties which are here very important. And we have such systems and styles and technologies follow very good software engineering principles. In the components we have encapsulation of functionality, encapsulation of data, or data which are coming as input are very well controlled. So we have a control about dependency between components. So this is like a positive part, how does it work. But now we come to a question here. What happens with when we have AI components in the system? Such cyber-physical systems, of course, these are the system where AI part is just a part, not a complete software. You may have some other applications which are like AI-centric, so the main functionality is one AI functionality. But even there, we have a lot of software around, but here, definitely not. So typical solution would be that we have components which are developed by AI, and are integrated in our system. And in this case, so we can say that we have encapsulation of AI-based functionality. We also identify and know dependencies between the components in the same way as before. But then there are two main questions which remain. So what is about this AI code inside the component? We don't have any control. Of course, we can use it as a black box, and we know principle of black box, but in many safety critical systems, black box are not really allowed. They are used as a black box, but actually analyzed very thoroughly before, so that some properties, like safety properties, are ensured. But then the question is, what about data? We have some data coming here, but what about data we have used in the development of these components? And what happened with our AI-based system now? So we will see that we need to introduce a lot of changes to make it work. So of course we have collecting data, analyzing data, we have computation, we have control the system, but now it's several order of magnitude about data collecting, about analyzing, about computation. We had further communication with the cloud and getting and sending information, but now we have to send much more data. We are also sending the data which will be used in our development system for training and for improvement our AI components. And of course, when we have the updating the system, then we are updating also these AI-based components. So we can say that in difference or in addition from the standard functionality which such a system has, we have processing of large amounts of data, and we have a large computational requirements. And can we solve that with our architecture? And the answer is no, because the requirements for processing data and computation are much more larger, and that's not manageable by this architecture. So instead, we can have architecture something like that. So instead of having small and efficient execution process units, which we have in this ECU, electronic control units, we need very powerful executional units. So we need like powerful CPUs and also GPUs, graphical process units, for performing parallel computing, which we are using in ML computation. But then also, in addition to that, some of the computing can be moved directly on the level of the sensor level, which can perform a lot of computational work, for example, recognition of the objects, which can be done directly on the sensor level, and in this way decrease the communication through the bus to these main computational units. So you can see that's quite a big change, and it is a question if such change is possible to make in an incremental way. like having the existing structure and then adding new computational units, or you need to start from the scratch. And of course, it is easier to start from the scratch, and that's why we have the systems like Tesla, which is completely new architecture. And for other companies which have this architecture have much more difficulties to switch to the new architecture. Then, of course, we have also cloud computing part, which is included in the process. Okay, so these challenges, which I already mentioned, are also related to the development process itself, because, of course, we have a separation of the processes, like for training and then development of software from execution. But we have introduced new functions, in particular because of, in principle, lower reliability or uncertainty of the result. We have to have new monitors in the system. So there are new challenges, not only in technology challenges, but also in the development process. But here I would like to say some few, very fast, some few fundamental problems which we have with AI and machine learning technique, and in which way we have to mitigate. So if you look at a component, let us say, and we say we have control data, which we analyze by this component, what we don't have a control is how this data, which data is used while building up this model. And we have a situation that the algorithm, this component, so does not depend on the algorithm itself. It depends on the data, and the data is uncontrolled. And that is a break of one of the basic principles in software engineering. You separate data from the algorithms and use algorithms to prove them for any data, or you define the scope of data. That's not the case here. The second problem is that, okay, similar to other software, it's not, AI-based functions are not continuous. So small change of particular data or particular feature characteristic can cause big change in the result. So that is one of the basic problems. And here there is a list of recognized problems which are related to managing data or using data in the algorithm. So one thing is related to use of many different data, different types of different accuracy, of different size, which requires a lot of work to adjust them to be used for preparing them for the machine learning, and that cause a lot of infrastructure type work. I will come to that one. The other is related between data dependencies, that data are dependent. And as you know, we have learned how to monitor and how to manage dependencies of software, like dependency between components. We have interfaces. We have programs like based on the Make, which manage dependencies. When we change the software, we rebuild the system and so on. Such dependencies are not well defined for data. We don't know yet what kind of dependencies we have and how we can control them. There are also problems with hidden feedback loops, in which the system is optimized to get the results for itself. So that's typical, can happen when AI component also generates some data and then actually generate the data, not which is the best for the function we needed, but which is best for the providing back input to this model, which will get then the best results. So there are several types of problems which are related to the data. But there are also other challenges, for example, which happen in the design of the system and the implementation. And that's because of this very heterogeneity of data and heterogeneity also in the quality and in experimental way of building up the models, in the sense that you are changing many things until you find, you believe, the best solution. It happens that there is a lot of software code has to be written to prepare and to build such models. So there are some experimental empirical data that 90% of code of AI-based system is actually glue code. And there is a frequent refactoring of code and a lot of re-implementation, and that makes the structure of such programs very, very bad and very difficult to develop and to maintain. Similar question is with versioning and variance. When doing experiments, many experiments are done, and these experiments, the models and data are changing, and code is changing. At the end, it happened that there are a lot of code which is actually not used in the current version, but maybe was used in some of the previous experiments. And have control of that, it is a challenge. So the challenge this of having this data when building up the system, and the data which are receiving, which the system received during the operation, that coordination, that's one problem. So even if we have like a local data which we are processing our system and under control, then of course a lot of this local data we use for machine learning, which we in some way have to provide for further learning. There are a lot of data which already have been analyzed. What is the relations between data? It's not obvious. So we don't know if there is some change here which causes that the system will behave completely differently than it was predicted through the training of this data. And that can cause that we have adjusted the system with a lot of parameters. For example, changing the thresholds, some decisions, and so on. And that requires continuous monitoring of the system and continuous test. Okay, so I would very briefly say about some empirical studies we did about what the companies and industry see, what are the most difficult challenges. And so we come to like this distribution showing that what is hard to solve, what is okay. My presentation has ended. I'll go back. I hope you can see it.
Yes.
Okay. What is hard to solve, what is easy to solve, and what has impact or what does not have impact. I will just show all different things, and for example, to show that effort estimation extremely hard. Very hard to estimate how much efforts and how much time the development will take. What is interesting that cultural differences between data scientists and software engineering is very big. So there is still a misunderstanding of the way how to develop the system. While data scientists, of course, focus on managing data and processing data, they have less experience in building and architecting the system, in difference from software engineering, which on the other side don't have understanding for example, working without having effort estimation, and also the matrices for measuring the quality of the systems are different. So these cultural differences is one of the problems. Also, here you can see also a list of different problems which companies met or expressed mostly in a different type of development. You have like from the experimental prototyping, not critical development, critical deployment, and then cascading deployment when you have like a full production, and in different phase of the development. So I will not go through them. There are many of them, but very many of them are related to software engineering and software architecture. And that has led to some work which we did in trying to identify what are the main challenges at the moment in developing such systems, and what software engineering and part of that software architecture could focus on. And here you can see the strategic engineering focus, which are related to these identified problems from analysis of different cases. And this is, we can group them in challenges related to data quality management, then to design methods and the processes, the model performance, and then in the runtime operations, like the question of deployment, and then the compliance with different standards and requirements and at runtime. And then for each of these strategic focus, we have identified a number of challenges which we can call the AI engineering, which are not AI questions, which are really questions of engineering. For example, looking at the infrastructure, about data versioning and dependency management, federated learning infrastructure, storage and computing infrastructure, deployment infrastructure. So that's related to infrastructure. When we come to development, managing data process and developing software, how to integrate that reuse of ML models and predefined ML models. What about the quality attributes, how to manage them? Integration of the machine learning models and software component models, and so on. And similar is in, if you look at the process, for example, this is typical example how to manage A/B testing, which is quite developed in today's systems, but how to do it with machine learning models, it's not yet clear. And then we have also realized that there are many challenges which are related to the requirements of the systems. So we know what are the challenges, what are the requirements, but we need new methods how to solve them. And so we look specifically for cyber physical system and safety critical systems. And then also coming to new type of the system, which are autonomously improving system, adaptable system using AI, so that can automatically improve themselves. For example, how can we generate data which are using for ML? How can we do automated experimentation, and so on? So this provides like
yes. So sorry, Ivica, to interrupt. Sorry to interrupt, Ivica. So just to tell you that we shall wrap up so that we have some minutes for questions. So sorry for that, but that. You know, yeah, thanks.
Okay, so the last slides, I will skip some slides which shows one example of like integration of systems. So so this is my conclusion. So you can see that there are lots of challenges, but this picture shows one very happy scientist when she made like a picture of the black hole. So that would be my message. There are a lot of things we need to do since there are many new challenges in software. Here I just mentioned some of them, and of course, many companies which are working today will not be able to cope with that and will disappear. But we as researchers have many new opportunities. So by this, sorry for expanding my time.
Thank you very much, Ivica. Thank you very much.
Oh, thank you.
So there have been a number of questions. Let's do in this way. I mean, my proposal, I don't know if you will have time later on, but what we can do, if you agree, Ivica, I can summarize now a number of comments. There's been kind of an interesting discussion. And if you want, we can create a channel for you with your name. Yes. That even if you are now busy, I mean, you can people can go and write other questions to you, and whenever you are, you can online or offline respond to the questions, because this is the whole purpose of a conference, you know. But unfortunately, timing becomes very strict. Exactly. So if you agree, I mean, we will create it, and you know, our colleagues can go there and write your questions, and then whenever you are free, you can go read them and you know, provide an answer, or even make a chat with them. For example, 11:30 we have a social meetup, so it's essentially some time where people is free. There is no presentation that can be used, but even, you know, whenever you have time. So let me just summarize a few discussion points that I could you know, put in my list. So Stefan at the beginning was asking why not a centralized architecture. There's been quite an interesting discussion between Stefan and Giovanni and also other colleagues on the need of centralized versus decentralized architectures. Then there's been a question by Jasmine about, and not only, also Anton Jensen was let's say working on this question and rephrasing about how to decompose AI design decisions in order to make some AI more individual properties. And from Patricia, how safety critical principles, if we can apply to those systems the same, I would say, safety critical principles that we were used to apply to previous systems. So what I would ask you to do, and everybody to do, is if you can have an overall answer to these high-level questions, then what we will do, we will copy those questions in your channel, Ivica, also yes. Put in the name of who was posing the question, so that even offline later on today or in the next days, you can go and everybody can go and pose other questions.
Yes, that's a great idea, and I will be very happy and exchange discussion with that. So that's a really great idea, and I'm very happy I can do it this morning. Yeah, definitely. So that's, and even we can continue during next days if through this channel. Of course, and so I will be very happy to answer and also to discuss some of these questions.
Perfect. So also, if you have any time availability, what you can do independently from the conference, parallel to the conference, is also to run your own. I mean, you're used to Teams, so you know that you can start your own meeting. So you can write in the chat that we are creating, in the channel you are creating, if you, for example, have a 30 minutes or 1 hour time where you can go and chat freely or make a call freely with anybody interested to talk to you.
Very good idea. Yes,
okay.
Very good idea.
So. Okay, so probably we will do the same for all the keynotes. And let me remember also to authors that you can create your own channel. It will be hidden from the others, but can be added. Okay, now in this case, we already created, so it will be visible to everybody. But if any other participant will create his or her own channel, it will not be immediately added to the list, but anybody can go and make it visible on his or her own list. Okay, just to facilitate discussion, which is, again, the real value of a conference. Okay. So what we are doing now, please allow us to switch to the next session, but we are going, while we move to the next section, the microservices, what we are doing, we are going to copy all the questions into the channel that has your name, Ivica. And if you have time now or later on, you can write directly in that channel and make an appointment or simply reply to the question. Okay.
Okay. Thank you very much, and
thank you very much
for listening.
Thank you very much, Ivica. I appreciate it. Bye.
Bye.
So the channel is already created. So sorry to make in this way, but this is a way to maximize discussion. That's essentially our goal. So we are going to copy all your questions over there, and you can again take a meeting with Ivica whenever it's available, and write directly on that channel information or defining a meeting time. So at this point, thank you again. We will move to the microservice session, and let us